All right, starting on time. All right. So how's everyone doing? Everyone feeling drag out? All four of you students. Feeling, oh, there's 5. Oh, wow. 6. They're coming on. We got twice as many virtual as we do face-to-face. I'm feeling the end of the semester malaise. It just always happens. You guys don't feel that way? You're like, well, I guess it's a little different as a student, as a faculty member. It's like, like for students, it's really stressful at final time, like near the end of the semester, and also finals, you're just like super stressed. For the teacher, it's actually, I'm usually ahead of the curve when it comes to like organization and getting material out. So like today's the last day of like material, like new material. And then like finals for a teacher, final is boring. And then it's just like a crap ton of work to do, but it's not like, it's like slow grading, you know, but it's not stressful. It's just a lot to do.
Boring.
Yeah. And you submit your grades and you go out drinking.
That's what all teachers do.
A lot of them do. Probably around 2/3. So anyways, here's a comic here. You see here's an s orbital, here's a p orbital. What's it? This is a 1s, this is a 2p, and this is a 3dz squared. And then you have an sp. So hybrids only. Kind of thing. What was it? Orbital parking lot. So says that chemists don't have humor. We clearly do, but it may not be the best of humor. So today's the last day of new material before the semester. And I have a feeling we'll finish class early.
You said I have a feeling we'll finish class early.
Yep, that's what I.
Sorry.
Kiana or Emma? Yeah. Yeah.
Sorry, it's my AirPods. Sorry.
No worries. No worries. Of all the things to say, repeating me is not the most embarrassing thing. But so you'll finally learn the truth. And here's the truth. So when you have one atom approaching another atom, I'm doing this for the Zoom, people can see. So you have an atom that has a nucleus, a positive center, and has an electron cloud. So as the atoms approach each other, the electrons feel the attraction to each other's nucleus. So the electrons feel attraction to each of the nuclei, and they also feel repulsion from the electron clouds. Plus you see the electronic field of the nucleus, and you see the electronic and magnetic fields of the electrons. And for bonding, it's mostly electronic field, by the way. So, but what happens is that and remember, electrons exist in discrete energy levels. And with all this interaction, the energy levels change. And so some go up, some go down, and enough of them go down, and the energy, and if the energy levels go down, and they can populate, and the electrons can populate them in a configuration that's energy favorable, it's going to bond. In a molecule form. Molecule means stable group of atoms. If it's not energy favorable, it won't form. And so all these other rules that we have, the octet rule, and then the shapes are VSEPR, the shape, that VSEPR is mostly correct. But really where the bonding, it all comes from, it comes from the electronic energy levels and the interactions of electronic and magnetic fields. So, I mean, that being said though, I mean, it makes sense, but it's also, the math involved in that is really, really crazy. So you don't learn about the math until your junior year or above, and you can study this your junior year and above. You get a little bit more if you take organic. Out of curiosity, is anyone taking organic? And well, I mean, not next semester, but in, like, you know,
the future.
Yeah, maybe. Oh, we got a maybe. So anyways, so like I mentioned, for you can kind of, oh, and what I'm going to teach you today is actually it's an approximation called the linear combination of atomic orbitals, also known as LCAO, linear combination of atomic orbitals. And so, for instance, for diatomic hydrogen, again, you have two atoms approach each other. What happens? And so the z-axis for me, this is the energy levels, and here are the electron energy levels. What happens when they come close to each other? They split. So here is even, here's two 1s orbitals, and they interact. The s orbitals disappear, and they form molecular orbitals. So these are new orbitals. They're not atomic orbitals, they're molecular orbitals. And you can model it by looking at the atomic orbitals if they subtract in phase or if they add in phase. So the top is subtracting in phase, and the bottom is adding in phase. So, and also it's like the waves. So if you remember, electrons can act like waves. So this is one of the ways they can act like waves. So you have a bonding orbital and an anti-bonding orbital. And actually, for all the math, especially for the diatomics that we're going to talk about, it works exactly this way. So because the molecules are just so symmetric. So it works exactly this way. So this is not a half truth. This is the full truth. So, well, it's about time, I mean, and you can see this. So you can have, when they subtract, you have destructive interference. And when you add, you have constructive interference. And we call the constructive interference, we call these orbitals bonding, and that's a sigma. A sigma is between, along the internuclear axis. So the bonding is happening between the internuclear axis. So it's a sigma bond. And not listed in the book, but you might see the letter G underneath that. And G stands for Gerade. That's German for symmetric or something of the sort. So meaning it's specifically symmetric upon inversion. Meaning if you look at this shape and you compare here, and if you put this through an inversion center, the inversion center is here. And if you look here, if this is symmetric upon inversion, it's Gerade. It's G. And here is the anti-bonding orbital. And let's do the same thing where you have this point and you put in the inversion center to here. And this is asymmetric upon inversion. And so we give this the U symbol. That means ungerade. That means not symmetric. So in German. And but you also see here's regular sigma and here's sigma star. Sigma star the star means anti-bonding. So actually this orbital, so if this is higher energy, this one here, the ungerade, the anti-bonding, it's high in energy, it's higher energy. And you can see anti-bonding orbital, and here the bonding orbital is lower energy. So
Are all diatomics destructive?
well, they're going to have both constructive and destructive. So even more so when we talk about the higher, like the period 2, because you have p orbitals you can do as well. So, and let me start another concept. Hopefully, and hopefully this isn't blowing your mind too much. You might feel like a little bit like my mind is being blown as you're going this class. But don't think too much about that though, because what you have to understand at this point in time is very simple. So in the bond order is easy. It's the number of bonding electrons subtracted from the number of anti-bonding electrons, that quantity divided by 2. And if it's a positive number, it's going to bond. If it's a negative number or 0, it's not going to bond. So let me show you this with the hydrogen atom or the hydrogen molecule. So you have, and so remember the y-axis here is potential energy. And so you start off with two atomic orbitals in the 1s orbital. And as the atoms approach each other, they form the bonding and anti-bonding orbitals. So the atomic orbitals, they go away. They're no longer there. They disappear because they are no longer, well, they don't exist. Atomic orbitals exist because of the proton attraction and the electrons interactions with the protons, and also the interactions of the electrons with each other. So, but the atoms are close enough now. You have a different issue where you have two atomic centers now, and you have electron cloud around these two atomic centers, and the new molecular orbitals form, and just the same rules as before with the Aufbau or building up principle. You put two electrons then in the lowest energy state, the sigma 1s orbital here. And the bond order, so we're going to do the bond order. So BO in chemistry means bond order. Number of bonding electrons, we have 2, and number of anti-bonding electrons, 0. This quantity divided by 2, this equals 1. So it means H2, which means H2 is single bonded and it's stable with a single bond, not surprising. This is same, Lewis theory says the same thing. So what about helium? Why doesn't helium bond? So if two helium atoms approach each other, what happens is, so same idea, you have 4 electrons and you have 2 molecular orbitals. So 1, 2, 3, 4. And the bond order now is number of bonding minus number of anti-bonding divided by 2, which is 0 over 2, which is 0. Which means helium-2 does not form. So not surprising. But what about helium-2 plus? Let's say that there's somewhere that has a lot of helium that's really hot, like, I don't know, the sun, or it's feasible that you would have some ionized electrons. So the same thing, helium-2 plus, right? So helium has 2, we have 2 heliums, 2 electrons, minus 1 for the plus. This equals 3 electrons. So we have 3 electrons to place, 1, 2, 3. And then the bond order is equal to 2 bonding minus 1 anti-bonding divided by 2 equals 1/2. Meaning that there is a positive bond order. And because of that, we should see helium-2 plus, so that we should see this molecule form somewhere like the sun. And we actually do see this. There is helium-2 plus molecular molecules in the sun, at least around the photosphere, that we can observe. And remember we talked about atomic spectroscopy, that you can each element has its own sort of fingerprints. So the same thing with molecules. These are energy levels. So helium-2 plus has energy levels, and we can do spectroscopy on it, or we can observe. So same idea, that you can have excitation and relaxation, and when it relaxes, it emits a photon. Same, so we can look for this photon, and if we see that photon, then that means that we found the identity. We found the fingerprints. We found the identity of that ion or that molecule. So we actually do see this in the sun. And if you wonder why, with space telescopes and space probes and stuff, they're saying like, oh, the atmosphere, it was big headlines. I remember there's a lot of methane on Uranus, for instance. And you're like, it turns out NASA says Uranus is full of methane. And how do they know there's methane there? And the reason is because of the molecular orbitals. They flew the probe by the with the sun, and as the sun went through the atmosphere, they can probe the atmosphere using sunlight, and they found holes in the spectrum where methane absorbs, and like, okay, without a doubt, there's methane here. So that's how they can do that. And then also the James Webb Space Telescope I sent you. That's really exciting news. It's supposed to go up on the 22nd of December.
Oh, the last time?
Yeah.
When will it be, like, ready to be used? Like, same thing?
No, they got to put it out. It's going to be far Earth orbit, and then it has to open up.
That's really exciting.
So it's not going to be that day. It's gonna be a long time. Like a long time. It'll be like a couple weeks or a month.
How much bigger is it than the Hubble?
I don't know. So Jenny would know, or I should say, Dr. Professor She should know. Has she talked about it in class? Okay. Yeah. Okay. So that's helium-2. So what about other molecules? So lithium, dilithium for you Star Trek fans, right? So dilithium, it's going to be 2 times 1 electron. So 2 electrons, and that means, so diatomic lithium, it turns out in the bond order here, it's going to be 2 minus 0 divided by 2 is 1. So this says that dilithium exists. And you know what? Dilithium does exist. Exists in the gas phase. So you can have dilithium vapor. Lithium, though, in the solid phase will condense. So it won't form, you won't have dilithium liquid or solid. So dilithium only exists in the vapor phase. So, but you do see this, and we do see dilithium. And of course, this goes against much of what you're asking about the telescope, Eli. Yeah, it's going up on December 22nd. It's scheduled right now. So if you, it was originally scheduled for the 18th, but when they were moving it, they banged it, and they took it apart to make sure that nothing was out of place. So the problem with this telescope is it's out of the range of doing human maintenance on it. So we don't have a space shuttle anymore, so we can't go far out. We only have rockets. Our capacity for human space travel right now is only to the space station. So we can't go any further than that. And we don't have the space shuttles anymore, so we can't go very far. But space shuttles are not very good for space travel anyways. So, but anyways, yeah, that's diatomic lithium. And so if you, like I said, Star Trek, or a Star Trek nerd, that's how they run their warp drive, and so it does exist. Now diberyllium, so just one over on the periodic table, right? So you have hydrogen, lithium, beryllium, so number of valence electrons. Beryllium has 2, so 2 times 2, we have 4 electrons, so 1, 2, 3, 4. And so, which means in the bond order, it's going to be 2 bonding minus 2 antibonding divided by 2, which is 0. So diberyllium does not exist. What if, for instance, though, what if we had diberyllium plus, and with diberyllium plus, this would become a 1, and then this would be a half. And yes, we do in fact see diberyllium plus. So we see some of these molecules here. Oh, and I haven't mentioned before, so dilithium is going to be diamagnetic. And beryllium plus, this is going to be paramagnetic because of the unpaired electrons. So meaning that diatomic lithium does not respond all that much to an external magnetic field, but diberyllium plus does, as will dihelium plus. But hydrogen normal H2 plus, normal H2 will not, H2 plus would, but normal H2 hydrogen will not, because the electrons are all paired. Okay. So how are we doing so far? Any questions? So I remember when I studied it, I was reading about this when I was taking chemistry in high school. I thought it was the coolest stuff. I was like, this is so awesome. Sorry if my voice is bland. I think this is really cool. It was just like, wow, it's blowing my mind. Okay, so we've talked about two s orbitals, and the two s orbitals come and they form, the anti-bonding orbital and then the bonding orbital. It looks like a surprise face. But the other way I thought about it, if you want to think of it another way, and I can mime this. So the bonding orbital, so it's like if you have two, I can't split myself, of course. So if you have two people, the bonding orbital is like big hug, right? So we're bonding. We are really bonding right now. The anti-bonding orbitals, meh, meh, right? It's just separation, right? So that's the way I always kind of saw it. So, sigma, remember sigma means between internuclear axis. So if we have two p orbitals come together, you can kind of have them bond. So that's your big bear hug. And maybe it's two cats hugging and their tails are sticking out here or something, I don't know. So two human cat hugging, bonding people with their weird tails sticking out. Also looks like a Tootsie Roll. Right, so that's your bonding orbital. And your anti-bonding orbital, this is, I don't want to see you, this is the, nope, get away from me. You're ugly, yes. It's not you're ugly, you're repulsive. It's repulsive. And also similarly, if you look through an inversion center, the bonding orbital is symmetric, so it's Garada. And if you look inversion center through an anti-bonding orbital, it's asymmetric, so it's Ungarada. So this is a sigma orbital. What about the pi bond? So remember, pi is above and below. So here are two p orbitals, and you can have the bonding orbital, a constructive interference, where you have a molecular orbital that forms between the two atomic centers. And then you can have the anti-bonding up here. But something to note though, what's interesting about the pi bond is, if you look at an inversion center, the bonding orbital is asymmetric. It's the Ungarada, it's the anti-symmetric. And then, but also the anti-bonding along the center, it's symmetric, it's Garada. Why am I telling you about the symmetry? Because it matters for certain properties, especially spectroscopy. So Raman, a technique called Raman spectroscopy, will work for the anti-bonding orbital, but Raman will not work for the bonding orbital. And also, if you've ever heard of nonlinear optics, there's certain things that happen with a technique called nonlinear optics. It's where you can have photons add an energy. So meaning like if you look at yourself in the mirror, so what you see is your visible, like, so when you look in the mirror, right, light comes, hits your face, goes to the mirror. The mirror it's silver or aluminum metal typically, and you have an electronic cloud here. So when the image of your face goes to the mirror, the electron energy levels jump. So the energy levels jump, absorb the photons, and then they go back down and they emit the photons back out. And so your eyes, what you're seeing is when you look in the mirror, you're seeing the light hitting your face. That light then goes to the metal. The metals absorb the energy and then re-emit the energy, re-emit the photons, and it comes back to you.
Is it positive feedback loop?
It loses some energy. There's some energy loss. So, and mirrors a lot of times emit slightly in the red. So that's why the image, if you look at, like, if you have two mirrors, it looks kind of green. You emit slightly in the red, and but it's pretty efficient. It's on the order of 90-ish% efficiency. So, and gold especially, gold is very good for infrared light. That's why the James Webb telescope is gold. Silver works a little less. It works good, but not as good as gold.
So when you look in the mirror, the electrons just jump.
That's before, usually. Well, that's a complicated question.
Sorry.
I can tell you, but it would involve using a Feynman diagram, and I can tell you after class if you're really interested.
If you want heat.
Yeah, that's gonna take a while to explain. Short answer is yes. If you want your nickel answer to a nickel question, yes. And so here is the z-axis. So what about into the plane? You can have the same thing, but it's just shifted axis. So it's very symmetric for the two p's. So let's see if you're following. Which one of these has the highest bond order? For is it diberyllium, diberyllium plus, diberyllium plus 2, diberyllium plus 3? Let's see if you're following. So beryllium has 2 electrons, so we have 4 electrons in. So many people think A, B, C, D. Okay, so here is beryllium 2. And the bond order is 2 minus 2 over 0. Oh, no, I'm sorry. That would be infinite. Over 2. This is going to be 0. So let's do diberyllium plus. Diberyllium plus would mean that this is 1 and this is a half. So bond order is 0. This is a half. So let's do plus 2. So plus 2 is that. And so bonding 2, antibonding 0 divided by 2 is 1. Bond order is 1. Then let's do diberyllium plus 3. You have 1 electron. This is 1/2. So 1/2. So the highest bond order is diberyllium plus 2. Do you see the logic?
Yeah, I was putting more electrons with the plus.
Yep. Okay. So this is something that you are not expected to memorize. This is, should be available to you, and there are open book tests, right? So here are the electronic energy levels for the rest of the 2p's. So, and there's something interesting after nitrogen, there's a switcheroo. So I mean here, if you see here, well, it's the same for each of the 2s orbitals. So as 2 boron atoms come together, they form the molecular orbitals. You can see the bonding 2s and antibonding 2s get populated, and then the pi orbitals, the bonding pi orbitals with the 2p are lower energy than the bonding sigma orbitals for the 2p's. And this trend continues on through nitrogen, but then for oxygen, when oxygen is there, the sigma bond between the p orbitals is lower energy than the pi bond. So at least for the bonding orbitals. And the reason for that is because, remember, when you have 2 atomic centers come together, there's interactions between the electrons and protons, electronic field, magnetic field, and then the energy levels form. Well, it turns out for this one, and this is mostly actually from the Zeeman effect from the magnetic field, the electronic effect is a little bit stronger. That's also known as the Stark effect. Electronic effect in general is usually a little stronger for bonding than the Zeeman effect, which is magnetic field. And in this case, the magnetic field causes these 2 orbitals to switch in energy versus this one here. You don't have to know that. It's just, but that's the reason why this happens. And so, but here are the electron energy levels then for certain molecules here. And so something to note though, if you look at diatomic oxygen, so looking at this diberyllium, so we have unpaired electrons, this is going to be paramagnetic. These two here are going to be diamagnetic. Diatomic oxygen is going to be paramagnetic. Fluorine is going to be dia, and dineon is just not going to form because of the bond order. So the bond order, what I mean by this, so if you look at the bonding electrons and the anti-bonding electrons, so I can use colors. So I'm doing the bonding orbitals in yellow, so the bond order, and this is for diboron. There's going to be 4 bonding electrons minus 2 anti-bonding electrons divided by 2, and that's going to be 2, 2 is going to be 1. So the bond, there's a single bond, if you will, between diatomic boron. And of course, this also breaks the octet rule, right? I mean, this is, but diatomic boron does form. So it's one of those things that does form. And so, but predicting properties, diatomic oxygen is going to be paramagnetic. And this actually was the reason why Lewis theory. So Lewis theory suggests this. And here's the Lewis structure for diatomic oxygen. And it suggests that everything is paired. And the pi bond there between, because the diatomic oxygen, meaning it's going to be 1 sigma, 1 pi, and 2 electrons in the pi bond, everything's paired up. This should be diamagnetic. Oxygen O2 gas should not interact with an external magnetic field, or a liquid oxygen for that matter. Well, guess what? Liquid oxygen does respond to an external magnetic field. And because of that, it means Lewis theory is wrong. It's completely wrong. It's couldn't be more wrong, and its name was Wrongstein. I had a colleague that said that. It wouldn't be more wrong if its name was Wrongstein. So, and that also means, because science, the idea is that once a better theory comes along that predicts more things that are proper, the old theory is gone, the new theory is in. And molecular orbital theory, quantum mechanics, all the sweet stuff that came with it is now the dominant theory, and it still is to this day. This happened in the 1970s. So, gosh, like 50 years ago. But yeah, I mean, obviously, we know now without a doubt that Lewis theory is wrong. Why do we still teach it? Because it works most of the time. Yeah, it works for organic chemistry. Most things with organic chemistry. I mean, there's some fine points that it doesn't work. But I mean, like for me, I can tell you right away if I'm going to be allergic to a drug because I have a sulfa allergy. So whenever the first thing I did when I heard about the COVID drugs, I looked up their Lewis structures, and I can take both of them. Actually, I can take all of them. I can take remdesivir too, but that one's going to go away. The 2 oral drugs. I know I'm not going to be allergic to them, or at least not because of the sulfa allergy. So I can tell right away using the wrong Lewis theory. But Lewis theory works very, very well. And molecular orbital, it works most of for most everything, but there's some points that don't necessarily work.
This one is new.
What, the new drugs?
No, the new molecular.
Well, yeah, it's pretty old, but yes, the molecular orbital theory is the most proper. So other things though, has anyone ever seen Aurora Borealis? So you have seen that. It's really pretty. You can see, well, with the magnetic field of the Earth and then the sun's radiation, you get certain colors. and the colors come from N2 plus and O2 plus. These are the primary ones. I think this one's yellow. I'm not sure. I guess I could always just ask. What are the colors from the northern lights come from? Doesn't tell me. Okay.
Wow.
Okay, well, Siri's not telling me. That's okay. I know they come from N2 plus and O2 plus. I forget which colors are from that though. I remember seeing the yellow, green, and a little bit of like kind of fuchsia, purple, pink. And I think the yellow is from the N2 plus.
It's not blue or green. Or into the two plus.
I saw what do you have you seen it? I saw mostly yellow and green and a little bit of like purple-ish pink.
Oh, I didn't actually see it. I don't know about
Okay.
it.
They're really pretty.
That's in Canada.
Why isn't Alaska?
The last one.
Yeah. It's anywhere in Norway. I mean, apparently Norway and Iceland are good places to see it too. But I've only been to Iceland in June. Okay. Questions so far? All right. So there's types of problems you could do. Draw a molecular orbital diagram, determine the bond order for the N2 minus ion. Do you expect the bond to be stronger or weaker than the molecule? Is it diamagnetic or paramagnetic? So N2, nitrogen, remember, has 5 electrons. So 2 times 5 plus 1 for the negative sign. This is 11 electrons. And here is, you would just get this from, here is nitrogen's here. So same idea, build it up, 11 electrons, 1, 2, 3, 4. Then Hund's rule, 5, 6, 7, 8, 9, 10, 11. Okay, so the bond order. So the number of bonding, I'll do blue for bonding. So number of bonding, we have 8 electrons. 8 electrons minus the number of anti-bonding. Oops, I missed that one. Three divided by 2, which is 5 halves, which is 2 1/2.
Is that because it's not symmetric?
This is very symmetric.
There's two orbitals there,
Which 2 orbitals?
the sigma asterisk, and then pi asterisk two.
It has to do with the 3 dimensions. So, because when you have 2 s orbitals, their s orbital is always positive. So you can either add them or subtract them. So you're going to get the hugging or the meh, sigma star. The same thing is true for the p's, but remember the XYZ axis, you have a p orbital here, and you also have a p orbital, I guess no, that would be along the internuclear axis. You have a p orbital here, different orbital. So you're gonna have a bonding orbital, and you're gonna have an anti-bonding orbitals. So this is gonna be your sigma and sigma star. Oh, I'm sorry, no, there's 2, I'm sorry, the pi. Sorry, I drew the sigma. I need to draw the pi. My iPad just updated, so my tools are. So the pi, let's see here. You're gonna have the bonding is gonna be, so it's gonna be along here and along. You're gonna have here I'll do it in yellow. You're gonna have the bonding orbitals be here like that. And then your anti-bonding orbitals, you're going to have one sign like this, and then you're going to have the opposite sign be like that, all along the plane, the XY plane for that one I just drew. And the other one, oh geez, using this orbital, that is going to be the XY plane. No, I'm sorry, the XZ plane. The XZ plane, and you're going to have along that one, and then along, oh no, I'm sorry, this is the D orbital, geez. I'm drawing. Gotta draw another one. You're gonna have this one here. You're gonna have a bonding here, like that. And then you're gonna have an anti-bonding where it's like this, because there's just the 3 dimensions. Sorry, if that doesn't make any sense, that's okay. But
I was wondering why you have 3 electrons that you subtract. And it's because they're antibonded.
yes,
And what makes them antibonded? There's just going to be.
because this one has a star.
I know, but
What makes it has to do with the relative energies. Like, remember when we had like 1s, 2s,
right.
2p?
And now we have 2 sets of orbitals because we have 2 atoms.
Well, they're not 2 sets, it's 1 set. The atomic orbitals go away and they're replaced with molecular orbitals.
Right.
Yeah. And these these are just degenerate energy levels, kind of like you have the 2 p's, you have 3 2p's, you just have 2 pi 2p's. These are just degenerate orbitals, just like you saw with the atomic orbitals. No, it's kind of weird when you first get it. How do you get 2.5 out of 5.5? So that's just the Planell division. 5 by 2, right, is 2. 2 times 2 is 4. Subtract, you get 1. So it's 2 remainder 1, right? So, and then, so it'll be 2 plus 1/2. The 2 remainder 1 equals 2.5. Or you can also think of it as 2.5.
To answer the question,
It is paramagnetic because it has an unpaired electron. Yes, as an unpaired electron, so it's paramagnetic. Paramagnetic. Need to enunciate. What's that?
pretty complicated.
That's why we teach it at the end.
It's like, here you go.
Good luck. Merry Christmas. Don't fail. Okay, no, it's not. So, but I mean, this is the level you understand how, if you can count, the number of electrons, you can populate them using the building up or Aufbau principle, and then you can determine the bond order from those electrons and determine if it's paramagnetic or diamagnetic. That's all you need to know at this point in time.
And then this is probably like entry level for next semester.
We don't use this very much next semester, but we do the Lewis structures a bit, and we do the mole calculations and stuff is universal. You always have to do the stoichiometry and the moles and the main reagents. Thermo comes back to haunt you again quite a bit, but not too much. A little bit of Lewis theory and molecular orbitals stop here. Same with the quantum. So. All right, so recap with this one. Determine the bond order for diatomic nitrogen -1. It has 11 electrons, so you populate the 11 electrons, and it has 8 bonding, 3 anti-bonding, and that corresponds to a bond order of 5 halves or 2.5. And since there's an unpaired electron, it's paramagnetic. So that's how you do that. Questions with that? Okay, let's see if you can figure this one out. O2 plus, diamagnetic or paramagnetic? Oxygen normally has 6 electrons. Although you could probably answer this almost immediately. How many people think it's diamagnetic? I think it's paramagnetic. Okay, both. Why would you even be able to just, do this without even thinking?
It's five.
Yes, it's an odd number of electrons. Yes. Because we also have 11 electrons. And actually, we just did a problem that has 11 electrons. It's going to be the exact same thing. Actually, yeah. No, I guess it's not. They split. Sorry, it's isoelectronic, but not iso in terms of the electrons. Anyway, so you have 11 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That looks like it's pointed. It's like, there you go, I'll touch it, point down. So we have 11 electrons, and it's definitely paramagnetic, but because there's an odd number, it's going to be one to be unpaired. So questions with this? All right, so this is the level you need to know for the final. Now, what you don't need to know are some other fine points. So how about heteronuclear? So far, we've done homonuclear, so same nucleus. What happens if it's heteronuclear, different nucleus? And if you look here, so like for nitrogen monoxide, and here's the Lewis structure for nitrogen monoxide, by the way. And if you look at nitrogen monoxide, here are the atomic orbitals for nitrogen. And notice that the oxygen has lower energy atomic orbitals. It's not as symmetric. And so then when you form, these are still pretty symmetric, but it's not going to be the same thing as a homonuclear. And it forms slightly a little, like kind of looks a little skewed. But it still forms the same molecules, or so similar molecules. And if you look at this, though, if you look at the bond order, so here are the anti-bonding, and here are the bonding orbitals. So the bonding orbitals, you have 8 bonding minus 3 antibonding divided by 2, and you see a 2.5 bond order for this. But the Lewis structure would imply that it would be a double bond. So you're actually slightly more bonded in molecular orbital theory, where your molecular orbital theory is suggesting a stronger bond strength than Lewis theory. So that's another difference here in the theories. And the one that's right, it's molecular orbital theory. Oh, and the other thing I wanted to mention, so when it comes to breaking bonds, so if you want to break bonds, there's 2 ways to break bonds. One of the ways is to remove electrons. If you remove enough electrons, then the bonds will break. Can anyone think of another, maybe a little bit more sneaky way to break bonds? So removing electrons, what else could we do? You could add them, right? If I start adding electrons, if I add electrons to this molecule is going to fall apart. So one of the ways that that you can break bonds is actually adding electron density. So if you have a stable molecule and you hit it with a bunch of electrons, the molecule is going to fall apart.
You just
It's atoms,
atoms.
atoms and electrons and ions, atoms, ions, electrons.
Mm,
So, so this is going to become important, and so not this semester, but next semester. So like if you have water, for instance, and I know I'm drawing the Lewis structure, and let's say you've got like hydroxide ion. You can have the hydroxide ion could add electron density, and here you have a sigma and a sigma star. And if you add electrons to the sigma star, what happens is then this hydrogen pops off. So you can add electrons and then the hydrogen will pop off, it'll break the bond. So that's one of the ways you can break bonds is by adding electron density. So another odd thing with molecular orbital theory, it doesn't mean that I told you that the atomic orbitals bond, they turn into molecular orbitals. They don't always have to turn into molecular orbitals. They can stay atomic orbitals. So for hydrofluoric acid, for instance, this molecule, it turns out that only one of the p orbitals in fluorine, actually go through and make the bonding. Hydrogen, so we have the one s and one of the two p's, it forms a sigma bond, also an antibonding orbital. But the electrons that are around the fluorine, they can stay in their respective atomic orbitals. They don't have to all go into molecular orbitals. So, and the reason, and like, well, when do you need to predict? It's like, well, it depends on the circumstance. In this case, because hydrogen only has an s orbital, so this is the only type of bonding that'll go. There's not other orbitals to interact with the p's. So remember the n for hydrogen is only one. So the n, the principal quantum number, whereas fluorine has the s and the p's. There's four orbitals for it to interact with, and in this case, the electrons well, I guess it doesn't. It would probably form with the s orbital, which I think. I'm not sure actually. I'm not sure if the p or the s would interact with that. Either way, it forms a bonding antibonding orbital. Only forms one, and the other electrons stay in atomic orbitals. So, also polyatomics. Yeah. So, if you look at ozone, for instance, ozone. So ozone is O. I'm drawing the Lewis structure here. That's ozone there. So, and it's a bent molecule like this, and you have the p orbitals of each of these here. And so the linear combination of atomic orbitals, and actually this is where this part of the theory breaks down. It doesn't work as well as you go further away from this, but you have a definite bonding orbital here. So the bottom one here, this is definite bonding orbital when all of the p orbitals are in phase. So if you have two in phase and one not, that's a slightly higher energy, and then you have the complete antibonding orbital here. So, and with this one here, you can have a node on that side where I've had it in green. You can also have the opposite where the node is on the other branch there in red. So actually these two energy levels are degenerate. So, and each of the oxygen is going to give 2 electrons to it. And so you have the lowest energy goes down here, and then the other 4 electrons go on the next higher energy. And we also have a couple terms here. We have what's called the HOMO, the highest occupied molecular orbital is the HOMO. And the LUMO is the lowest unoccupied molecular orbital. So if you go on and go into organic chemistry, they'll talk about HOMO and LUMO. And that's what I'm doing right now is I'm prepping you for organic chem. I don't talk about this on my final, but the HOMO and the LUMO, and that's very, very commonly used in organic chemistry. So I have another cartoon for you that I saw. So
Stop.
oh shoot, there we go. So here is my other cartoon. It says, stay at HOMO, stay at the highest occupied molecular orbital. This is the highest occupied molecular orbital. Up there is the LUMO, lowest unoccupied molecular orbital, no electronic transition. So it's the stop. Preventing electronic transition. You can see here, this is these two are in phase, and the top one there, they're out of phase. So it's a higher energy anti-bonding orbital. So that's just, you know, chemistry, humor at its finest. Okay, I can't. Let's go front. There we go. That's one way to get around that. So there's a cartoon for you there. Okay, the last thing I want to talk about is I'm sure you've heard of a couple of molecules that are dangerous. One of them is carbon monoxide, and the other one is the cyanide. You know, when you think of carbon monoxide, you think of cyanide, especially cyanide. You know, that kills. They both kill. And do you know what happens with carbon monoxide and cyanide? Why you die? Suffocation. And why you suffocate? Well, the reason is because carbon monoxide and cyanide bind to hemoglobin stronger than oxygen. So hemoglobin is a really interesting molecule. So hemoglobin, actually, you have hemoglobin has 4 irons. So you have let me give you my PhD in chemistry ability of art. So a hemoglobin has 4 heme groups. And have you ever heard of the Beyond Burgers? Like Beyond Burgers, it's interesting for them because they figure out a way to make heme. So plants don't have hemes. Animals, we have hemes. You know, we have hemoglobin. So they figured out a way to make the heme protein without killing an animal. So in hemoglobin specifically, it has 4 heme groups attached together. So there's my drawing of hemoglobin. So if we're playing Pictionary, like that's hemoglobin, 4 irons with a big blob around it. So no, it's hemoglobin. Paris is the ion. Anyways, and hemoglobin is also a really weird molecule because it is actually as it's more oxygenated. So O2, it attaches itself to the iron, and the more oxygen that's attached to it. So this molecule with 3 oxygens, this is really easy to attract more oxygen to it, because when you have the hemoglobin, and I only have 2 hands, but like when you touch more oxygen, the molecule opens up, and it's actually easier for oxygen to attach to it. The more oxygen is attached to it, the easier it is to get more oxygen to it. And on the other way around, well, that's great because so as a human, or well, any animal that uses hemoglobin, so I guess octopi don't, but humans do, and most land mammals do. I guess only octopi, I think, are the only ones that don't use iron-based hemoglobin. They use copper-based. Yeah. Hey, they're smart, but our animals with the iron-based hemoglobin, we uptake oxygen really quickly. Maybe if you've been swimming and you held your breath for a while, have you noticed you come up, you're like, you're like, oh, I'm still dizzy. Oh, like, oh wow, so much better after the second breath. And 3rd breath, you're like, oh man, I'm ready to go back underwater. So actually, the more oxygenated your blood is, the easier it is to keep it oxygenated. So that's why our blood saturation is always at like 100, 98, 9, 98, 97. It should be really high. And then for humans, like when we start dropping to like below 90, or below 85, that's pretty scary. I mean, 85, you think 85 is pretty high, like you think I'm 85% away from perfect. Like that's pretty good. But when it comes to oxygen, like, nah, that's not good. So you want to be in the high 90s saturation. So, and if you're not in the high 90s, you usually feel terrible. So, okay, so, but oxygen then attaches, but the idea though, oxygen attaches to hemoglobin, but it doesn't attach very strongly. So it's not a super awesome bond. So iron going to hemoglobin, I'm sorry, oxygen going to hemoglobin and the iron, it's not like, I will never leave you ever again in my life. No, the oxygen attaching to iron and hemoglobin is like, hey man, you'll come along for a ride? Okay. And like, hey, oxygen, you want to leave? Okay. It's not a very strong bond. It's easy to form, easy to break. And the problem though, when you have carbon monoxide and also cyanide, iron, and where it attaches on iron has the d orbitals. So iron has these open d orbitals, and the same thing with these diatomic heteronuclear carbon monoxide and cyanide. The pi bonding, especially the anti-bonding orbitals, these are empty. You have these empty pi bonding orbitals, and then when they approach the electrons and the iron's d orbitals, they actually bond. So these open orbitals, empty anti-bonding orbitals will bond with the atomic orbital of the iron, and then electron density will be shared between them. Actually, so when you add the electron density, the bonding here, actually the bond order carbon monoxide goes down. So actually when you study we call them carbonyls, and you have carbon monoxide on this, the bond energy between carbon and oxygen in this molecule will go down when it's bound to iron or something else in the like a hemoglobin group, but it still binds here, and it bonds stronger than oxygen, and that's a problem. So patients, they die from suffocation. They just don't get enough oxygen. And the treatment, if you want to know, the treatment for carbon monoxide poisoning is actually give the patient oxygen. Actually, they usually also inject the patient with a little bit of lidocaine, because you can have some heart damage from it too. But cyanide, there is a cure for it. Essentially the same thing, but well, you can use oxygen. But cyanide, there is a way to neutralize the cyanide. I forget what it is.
You just try and get the oxygen to as many hemoglobin so it shuts down oxygen.
You just make sure that the patient gets enough oxygen, because the carbon monoxide can pop, it can pop off too.
Eventually.
Yeah.
It will pop up.
Yeah, just and then you want to make sure there's as much oxygen there, so that the blood will still be able to carry oxygen.
Will they just give them straight O2 or do they do like a mixture?
They'll give them a straight O2. So, and I'm done. So this stuff here with the back bonding and the homo-lumo and the heteronuclear, that's not on the test. The homonuclear, so homo, same nucleus up through the two P's, that is on the test. Knowing how to calculate bond order and magnetic, paramagnetic, you have to know how to do that. So those stuff, that's just extra, and I'm prepping you for organic chemistry. You take organic chemistry, so it's not like, hey. So I'm trying to follow the fine line between, not telling you too much stuff at the same time, telling you enough stuff to prepare you for the future classes. But I'm also telling you what I'm not going to test you on. So, questions so far? If there's no questions, I can end class early because I have absolutely nothing else to talk about. Oh, God.
Optimus Prime.
It does sound kind of like that. It's Decepticon. It's all right. In that mind, everyone is free to go.
With myself a beyond.
Thanks for the lecture.
Are you
Have a
okay?
good day.
So.
Bye.
If I eat meat, just get more iron than beyond meat, or will it be the same?
I don't know the concentration. I have to look at the nutritional information. I don't know how much they put in there. And different meats have different amounts of iron too. So like beef and lamb will have more than chicken, for instance.
Wait, say again?
There's beef and lamb have more iron than like say chicken. I mean, like you can't say meat. I guess whales have a lot of iron in them.
Yeah, because I've heard of iron deficiency from not eating roast beef.
Yeah.
You want to explain the mirror thing before I go?
Okay, sure. Sorry, Eli.
Unless Eli wants to talk.
Closed canceling has been enabled. Let me stop recording.